So good morning. We are in the GANS course Combustion Theory and Applications day 5. In this lecture today we will talk about the part 2 of laminar premixed flame. In the previous lecture we emphasized about the fundamental concepts of laminar flame, its characterizations, mathematical correlations through which we can compute the laminar flame velocity. Additionally, we found that certain correlations are important while we use that correlations as a function of pressure, temperature, equivalence ratio that characterizes the various characteristics during combustion if it is a purely laminar flow. Then in this lecture we will proceed further to bring out some other fundamental concepts that are of two categories. One is this flame arresting, second is flame stabilization. So in our previous lecture we emphasized that for a sustainable laminar flame we need to have a favorable pressure difference or pressure and temperature conditions so that continuous combustion is possible. In fact, we demonstrated that with respect to IC engine combustion for premixed air fuel mixture, in which it is emphasized that for a normal combustions we get a pressure trend as a function of time in a smooth manner. But however, when the favorable conditions is not there, this is shown as a pressure pulses, sudden oscillations when the peak pressure is reached. So this says that flame is already at elevated pressure and temperature and it has sufficient strength and it provides knocking. At the same time, if you want to bring this situation back, we need to have some other methods that we must avoid this knock through certain mechanism in which flame can be arrested. Of course, this flame arresting is not a typical phenomena for engines, but this arresting methods is very much required when you use this laminar flame for certain applications in terms of burners, cooking burners. So this arresting method is required that when the flame should not travel back or create a flashback for which we require to arrest the flame. In other words, we can say we must reduce its momentum to move further, to move backward. So that is one aspect we also require. Second aspect also is that for cooking type of application, burner applications, we require a continuous stabilized flame. So as long as we are supplying air and fuel mixture with appropriate compositions, we must get the flame. And second point is that the flame should sit on this burner surface. It should not be blow up, that means it should not go above the burner. At the same time, it should not create any flashback. So that condition we call as flame stabilizations. So there are certain techniques. This flame arresting method is dependent. First method is that first thing is that we should know that why we what are the different criteria in which we generate the flame. Particularly when you look at the kind of flame, and this flame has to be flame is, let's say in this SI engine case, the flame is propagating and you need to arrest it. So the arresting of the flame depends on the area in which this flame is moving. Then second method is that we can control these flame propagations by changing the composition of this unburned fuel air mixture. So that thing we can talk about in the form of flammability limit. The first one we can talk in terms of geometry in which the flame is propagating. So that is can be quantified by quenching distance. Another point is that whether we can create a flame or not, that depends on how much energy or ignition we are dumping into this charge. So that is criteria is that it's a minimum ignition energy which is required uh, to create that flame. That means we are giving sufficient strength to the flame so that it can travel on its own. So these are some of the methods which we can think of. Second is, in a classical way, we try to extinguish the flame. So extinguish method is simply dumping or cooling the flame through water. That is one aspect. So when fire is burning, we dump water so that it gets extinguished. Some cases we have fire extinguishers that can stop the flame propagations. So which means that diluents such as water, chemical compositions, or in terms of fire extinguishers which are in the form of halogens, they can alter the chemical kinetics. So basically, in totality, what we can say that the flame has to be extinguished under certain situations, which in which it cannot create the explosions. In other words, in a layman sense, we can say by creating these concepts, we are altering this chemical kinetics of the flame. So this is our three basic methods which we are going to discuss. So first thing that we talk about, the term called as quenching. So quenching term depends on a parameter what is called as quenching distance. This quenching distance is determined by observing the flame which is passing through a tube so that it does not flash back for a particular tube diameter, which means if you are looking at a flame with the flame which is passing through between two parallel walls separated by a distance d, and looking at a flame which is in this domain. So what we can see, there are two walls here, and we can imagine as if there is a flame and this flame is moving up. This dotted line shows a kind of a wall which is in the vicinity of the flame, and we call this as a adiabatic wall. And this slot have total energy which is entirely stored in the flame, and it is going up. So when it is going up, it is trying to bring the charge into it and getting it combusted, so that flow it is moving. So there are two parameters here. One is called as delta, and this delta uh, and other is the parallel wall in which the flame is moving. So there is a correlation between this delta and D. So there are two set of thumb rules which governs this ignition. First is that ignition will occur if enough energy is added to the gas to heat the slab about to heat the slab of certain thickness for a steadily propagating laminar flow to adiabatic temperatures. So once you put this minimum ignition energy, the heat which is liberated by these chemical reactions must be equal to the heat loss from this slab by the thermal conductions. So basically what amount heat is generated through this, it is getting taken out by the slab in which it is moving. So that's the wall. When you imagine that when you are this type of flame is propagating in a combustion chamber on the engines, the chamber gets heated and we require cooling. So that way but in this perspective what we say, that heat which is generated, it is getting consumed by this. Now if it has to be consumed, that means when if it doesn't consume, then strength of its goes up, and if it has to be consumed, because otherwise it will create a flashback. So in this perspective, in this philosophy, there are two parameters that are taken into account. One is, suppose a flame which is entered in a slot which is separated by a distance d in this case, and we can define this adiabatic wall adiabatic flame thickness delta. So adiabatic flame thickness delta means that flame is not getting cooled and entire energy is sitting there within certain vicinity of this wall, within the some vicinity of this thickness, and that thickness is very short, and that is called as flame thickness. And we also have, this means this is the maximum when you talk about adiabatic flame thickness, that means at this point flame has its maximum strength of heat within that volume, and this has to be distinguished or extinguished if the flame doesn't have to create a flashback. So for that reason we can these walls should be placed in certain appropriate locations, so that, and that distance we call this as a quenching distance, which means it is the minimum distance we must have that the flame cannot traverse back. So that way this quenching distance for the flame is always greater than the flame thickness. That means we cannot have so much this distance should not be so small, so that with respect to the flame thickness it should be higher than that. And this flame quenching distance is also dependent on the other parameters like pressure and temperatures. Now over the years the things are modeled in this case to find a suitable correlations between this quenching distance d and the adiabatic flame thickness delta. And here we define two parameters. One is this delta, one is this b. B stands as which is square root of b, and we have the square root of b into delta. Delta is equal to your thermal diffusivity with respect to ratio between the thermal diffusivity and the flame speed. B is just a number, just to give just to make a correlation such that the quenching distance and delta is adjusted in such a way that B is taken in such a way that quenching distance and delta gets adjusted among themselves. And further, we also, this thermal diffusivity is dependent on this pressure and temperature parameter, and which stands as a function which is a proportional to T to the power 1.75 by P. Then next point that we talk about in terms of flame arresting method is the flammability limit. For every fuel, there are two limits in which we can initiate the combustion. You must have known that for IC engine operations, we define this as a in terms of equivalence ratio. That means engine normally operates in the equivalence ratio between 0.8 to 1.2. That is one part which is effective for engine point of view. But with respect to fuel point of view, it is also possible to initiate combustion at much more lower equivalence ratio, which is also less than 0.8 also, and it can also go above that 1.2. But what we are looking at the flammability limits, the minimum limit, which is the lower limit for the lean mixture, and maximum limit for upper mixture. We say that above this mixture, we cannot make it with a very high fuel reach, so that combustion cannot be initiated, and we cannot have a number which is very lean for which combustion cannot be initiated. So that is the limit. We call this as a flammability limit, and normally this flammability limit we say phi, which is written as phi minimum. Let's say I'll put phi maximum So there are two ranges, we have minimum and maximum, and in this we call this as a flammability limit. A mixture that sustains the flame is to be flammable, and just by adjusting this flammability limit. So this particular curve talks about the flame temperature as a function of x, and it also we are looking at this delta, flame thickness delta, and here if you can see, initially when the combustion is initiated, temperature shoot off suddenly to a maximum value, and normally in this impulsive nature of the temperature rise, we define this adiabatic flame thickness, and the temperature reaches to a maximum. But however, we can have adiabatic flame temperature which is much above that, and when you talk about this as a flammability limit, we have to say that somewhere we are operating this as phi, and this side we can have phi minimum, this side we have phi maximum. Then other important point what is to be noticed is that there is a instantaneous axial temperature rise which is along the central line of the tube. There could be possible conduction losses along the wall, and many times what happens, the cooling effect of the products gases create an adverse situation, which means is that why the imagine that in a laminar situation, premixed flame, flame is moving forward, consuming the charge. Sometimes what happens, the temperature shoots up, and ideally temperature and pressure shoots up, and if the temperatures and pressure and shoots up in such a way that all those atoms, they started to recombine. For example, nitrogen started to recombine with oxygen or something. So it is expected that during the recombination they try to absorb energy. Through this energy absorption process during recombinations, it has a negative effect. That means flame is getting cooled because the environment temperature drops down due to reaction of recombination of atoms among themselves. So that is called as cooling of product gases, can create a negative temperature. Now when sufficient heat is removed and quenching criteria is satisfied, then flame does not move further. So the flame stops there. That means flame is sufficiently cooled. In other words, we say we have arrested the flame. The next category of analysis of flame arresting method is ignition. So ignition normally happens using a spark plug. The spark plug has certain dimensions of certain size or diameters, as if during a spark ignition what happens, we are this is we are creating a kind of and one simplest way we can create is a spherical frame. Through this thing, what we can say, we are dumping this energy through the spark plug, and for this spark plug has some diameter, and through this spark plug whatever maximum size we can create, that a spherical flame is based on its critical radius of the, which is with this spark plug we can create this maximum diameter of this spherical flame, that is called as critical radius of the plug, or in terms of flame point of view, that is the maximum diameter of that spherical flame. So there are some correlations that how we can find out the critical radius of this gas volume. This is modeled in terms of spherical flame, and it depends. Basically, all you need to want to know is that what is the minimum ignition energy which is required by the plug. To get this, we require the information about this critical radius for this gas volume, and this correlation says that this critical radius is square root of 6 into alpha d times SL. So here alpha d again depends on many parameters. Alpha d depends on the pressure parameter. Here this SL, this depends on the ratio of unburnt gas mixtures and burnt gas mixture. Then we have other terms. This in terms of this can be interpreted in terms of flame thickness, because alpha d by SL is delta. So through this we can find critical radius for a gas volume as a flame thickness of this spherical layer of this gas. Then we need to find out, that is a relation what is through which we can find out how much minimum ignition energy required for a self-sustained moving flame. So that depends on this, all these numbers: pressure, then thermal diffusivity, flame speed, temperature ratios, and so on. And here RB stands as the gas constant. This RB is one parameter like Cp by RB. Cp stands as the specific heat at constant pressure, RB stands as gas constant for the bond gas. This is calculated through ideal gas relations. Then next thing is we need to talk about this ignition analysis in terms of okay, this is already this I have already mentioned the effect of pressure on the minimum ignition energy is the result of direct influence and indirect influence in terms of thermal diffusivity and flame speed. So what we can say, this minimum ignition energy is inversely related to the square of pressure. So if you actually see here, PE, minimum ignition energy, is a function of pressure, but the pressure is implicitly involved in the calculation of the flame speed. How? Because this flame speed is the function of Tu by Tin, and which means that it also boils down that ignition energy is inversely related to pressure. Then we will move on to next segment, what is called as flame stabilization. In most of the combustion analysis, particularly cooking stoves and all, we require a self-sustained flame to remain, so that we can say that flame is sitting on the burner face. So there are two phenomena that can occur if there is flame is not stabilized. First phenomena is called flashback. Second phenomena is flame lift off. That is mainly two critical aspects for the flat burners or cooking burners. We also say that flashback can occur when the flame enters and propagates through the burner without quenching. So that means the flame doesn't see sufficient pressure difference to move forward, so it travels backward. Now while traveling backward, it sees that it doesn't have a sufficient slot diameter, and it follows through that slot in an effective manner. Through this we can get a flashback. So for that reason, which means that appropriate quenching distance is not maintained. So that condition is called as flashback. Other option is that through pressure difference. If the pressure difference is such that it does not, that means we need to have, if it doesn't have a minimum ignition energy, so through this, if he has more than this minimum ignition energy, it travels back. Also, the large volume which is there in the mixture, it can also create this explosion, because when it flashes back, all of a sudden it sees the large volume of charge. Hence, this flashback has to be arrested. The other condition, that is what we call as flame lift off, which means this is a condition when the flame is not attached to the burner, it sits at certain distance, and this is what we call as standoff distance. If this is your burner face and it is sitting some height, so this distance we call as standoff distance or lift off height. But however, this lift off condition has to be avoided, because that is not a case for flame stabilization. Why? Because this lift off situation allows the unburned gases to escape. That means we are underutilizing our charge. Although the lift off, flame lifts up to certain distance, but if it goes above that, it is difficult to create ignition. That means ignition is difficult to achieve for above the lifting limit. Then accurate control of position of lifted flame is difficult to achieve. Through this lifted flame, it will land up poor heat transfer characteristics. And when we have lifted flames, they are always noisy. The conventional cooking burners, you might say that we might have experienced about these cases when the flame is lit up, or we normally do not create, suddenly we switch off the burner and an abrupt noise pops up, which means that those cases are recalled as noisy situations. Now let us talk about flame stabilization in terms of flashback. So flashback, when you see this particular figure here, we see that there is a burnt gas and flame front is moving, and on this flame front we can say that at each particular point we can define certain velocities, that is on the flame front, but at the same time we can also see the gas velocity which is moving, and this profile can be linear, which means that at this wall the gas velocity is 0, and with when we increase to, when we go towards the center line, then this gas velocity is more. So one point, that means these two vectors or these two forces, they try to interact each other. When they interact each other, it creates the dominance of one with other. If the dominance of flame front is more, then it suppresses this, and dominant of gas velocity is higher, it pushes the flame. So due to relative dominance between these two, we get this flashback, and of course it is sometimes it may have, there could be a transient phenomena which arises, and with time it tries to settle down. And the next is and it also depends on the tube size in which the flame is propagating. So hence what you can say, the controlling parameters for this flashback is same as that of fuel time, equivalence ratio, flame velocity, burner geometry, and so on. So this is another figure which talks about the case study, just to give some trend of two types of flame, two types of fuels. One is a fossil fuel, methane. Second one is hydrogen. So basic difference while talking about or considering these two cases is that hydrogen has a large flammability limit, whereas methane has smaller flammability limit, which means in terms of equivalence ratio, there is a large window in which we can create the ignition for hydrogen, but there is a small window in which you create the ignition in terms of phi, equivalence ratio. So these two, and because of this reason we can say the flame speed in hydrogen is about 5 times faster than the flame speed of methane. So what it says here, this particular diagram, it is a generic plot, not in terms of quantitative manner, it is a generic plot. It talks about the gas input rate or fuel flow velocity with respect to primary air, fuel, and with respect to percentage of final primary or theoretical air we consume. So if you go along and if you show their trends, what it says is that we for a methane we have this flashback zone somewhere here, which means for flashback to achieve, we are in the our air requirement is very high, but in other case and also we have fuel requirement is very low. So that means that is the safe zone in which fossil fuels are operated, but that is not true for these things, because your flashback zone can happen any point with very small fuel flow input. At the same time, air requirement maybe close to 60% we can have it, and air is anyway available for the charge. So small quantity of fuel can lead to a flash zone area. This is not possible when we use the methane. Now when we say that flame is getting lifted from the burner surface, we can find a trace through which that if you keep on increasing the gas input rate or fuel velocity rate with this, you will find that with increase in the fuel flow rate, the theoretical requirement is less. So that means whereas in the, and this number is somewhere within this 60%, whereas for hydrogen it is much more higher. Similarly, we have lower regime in which the flame shows a different color, like we have yellow color here, we have yellow color here, and this is possible with 20% and here also close to 40%. So that way this gives you a domain in which we can design your area or geometrical area of that burner port. So here we have a large domain of design area for a stable flame, because that is what we require, and that domain that is a standard domain. Here we will have also for a stable flame, in this case we will also have a very much larger domain than this. Okay, that means for hydrogen lifting zone requirement is higher, whereas for methane it is lower, which means that we have a flexibility of larger burner area for hydrogen as compared to fossil fuel or methane. So this is one kind of advantage, but however maximum possible area for hydrogen we can define this and here this, but there are detrimental effect if the flashback zone is taken into account. Or in general, the basic summary is that whatever size you or design area or you choose for a stable flame, either for methane or hydrogen, the main intention is that it should have flash free zone during its operation. That is the requirement for a stable flame. Now another situation I have emphasized here, that flame is tried to lift up. Lift up, which means it's this, why it is gets lift up, because flame has sufficient strength. It does not get enough oxygen from the charge, and it gets oxygen from the diffusing air, which is outside the zone of, which is atmosphere. Assume that we have the burner face and flame gets lift up, so there is a stand-up distance between them. So through this you have atmospheric air running into it and oxygen gets filled up. So the flame plant gets enough oxygen to lift it further. But while lifting it further, if you see that at the same time you have gas velocity which is coming up, so they either try to diffuse or they try to get these things here. But if this flame trump lifts up with a certain limit, then it can say that this input charge gets diffused outside without getting ignited, because the flame plant has already traveled further and the energy is not in the vicinity of the surface, it is somewhere outside. So that way, if you look at in terms of this velocity diagram of laminar flame, this alpha changes. So alpha is no longer one particular thing, is that this condition has to be satisfied for between unburnt gas velocity Vu and the laminar flame velocity Sl. So they don't match, which means flame gets lit up. So there is a critical velocity at which flame gets lit up, and that when it crosses its critical velocity, we will have higher vertical flame lift off distance, and the flame until the beyond the above this burner surface. So this is, I have already explained, but the phenomena of lift off or blow off hose, that I need to emphasize. So lift off, I told you that lift off is that flame is getting lifted from this burner and sitting at somewhere. So that is the lift off. There is a situation called blow off. So blow off means that the gas velocity at one particular time, this gas velocity does not see the flame in its vicinity. That means input charge velocity doesn't see it in its vicinity, and so it could not be ignited. So when it doesn't get ignited, but it has a sufficient momentum to push the flame. It can push the flame, but it cannot ignite on its own. So that way we say that flame blow up condition is achieved. Now in heat transfer point of view, we say that this is a counter effect, or for which heat or radiation loss to the burner tube. So this view is analyzed, the heat or radiation loss. So ultimately this leads to a conclusion for methane and hydrogen is that the lift up operation for the flame varies as the function of primary air flow velocity, and methane flame is more towards lifting as compared to hydrogen. That is also true because hydrogen has very high flammability limit, wide range of flammability limit, and of course hydrogen has higher flame speed. So this is all about I need to discuss with respect to the laminar flame analysis. And this particular at the end of this lecture I try to emphasize that some numerical problems which highlights for a flat flame which is sitting on a burner, and we need to calculate, and one case study which is done for a methane air mixture, and the condition that burner operates is 300 Kelvin and 6 atmosphere, and we need to find out what is the condition for flashback, what is the mixture mass flow rate. That means you need to design this burner. When you try to design this burner, we are actually trying to find out what is the burner size and all. So first step, we need to find for methane air mixture what is their mass fraction of air and this mass fraction for fuel, and we need to find out also the density of unburnt gas mixture to obtain this mass flux. And this particular equations data either you can use this dependence of flame speed as a function of pressure, and using this one can find out these things one by one. First is what is the mass flux, second how we can find out the diameter ratio, which talks about the conditions when we have a non-lifting case, and other we have a the basically when the flame has to sit on this burner surface. Other case is what is the maximum distance it can sit on this. So this will give you the allowable tube diameter. Then another important problem that talks about the importance of flammability limit. For example, this says that in a corner of a room, in a cylinder, the propane gas leaks, and whether that leaking creates and can create an adverse situation or not. So to find this case, what we need to know, first thing is that we have to, from the data table, we need to find the what is the minimum and maximum flammability limit we can find out, particularly for propane. This we obtain from data. Now for these particular conditions, what is the value of phi which you need to find out. So in this case, you have given the size of the room, mass, temperature. We can use these ideal gas relations, find the pressure, and of course we have atmospheric pressure. Through this we can find out the mass fraction for the fuel, and here the fuel is methane. Once you know the mass fraction, correspondingly we can find out the air fuel ratio. So this is how we get air fuel ratio for this particular case. Now again, for methane air mixture, if you can look this balanced equation or complete combustion equation, we can find out the corresponding stoichiometric value, and for this case the stoichiometric value happens to be 15.6. So through this, what we can say, air fuel ratio and air fuel ratio actual and air fuel ratio stoichiometric. From this we can find out what is the equivalence ratio for this fuel which is getting leaked. That means this mixture, when it is leaking, it has the equivalence ratio 5, because when it is leaking, it is mixing with air, and it is mixing with air means at that case your equivalence ratio is 0.18. Then you have to cross check whether it falls in that flammability limit or not. So that way one can say that, and in this particular case we say that mixture does not support the flame. So this leaking cannot initiate a flame. When it cannot initiate a flame, we can say it is not a detrimental effect or adverse effect, or it does not lead to any kind of explosion. Sometimes also in our conventional cooking burners, we feel there is a leak through smelling, but that leak does not lead to explosion because it is in very low flammability limit. And when the flame it crosses this, when it comes to this higher flammability limit, it can create some adverse situations. So this is all about I need to discuss for today. Thank you.